And last night we were sitting around, as we often do, scientists, and we were philosophizing about how the internet has changed our lives. And usually before I give a talk, I do some research. So what I did is, Camille was telling me his daughter taught him how to use Google and aspects of Google. So I went to my room and I Google searched on images and Gil Navon. And so when you do a Google search on Gil Navon, on images, this is the picture that you find. This is one of the pictures. And you know, this is why Gil stays so young. He's always happy, he's always smiling. And so this is wonderful. But there are also some other interesting people who come up under Gil Navon's picture. I think you'll recognize this gentleman. So I don't want to make any political statements, but I didn't realize, I knew Gil was a very important figure in Israeli chemical circles. I didn't realize he had political influence in this country as well. And then you find this guy on your picture. So I think, Gil, I underestimated your international influence in the political scene. I invite you to do this. You'll find, if you do it about yourself, you'll find people's pictures you can never imagine ever wound up on your Google image page. So this is the topic of my talk. I actually changed it a little bit. I'm going to talk about endogenous cest agents. And I'm really the least, and the new is a very arrogant term. So some of them are new, and some of them are old techniques applied in a new way. And this is really the work of Elena Vinogradov and Gopal Varma, and I had a role in this, a very important role. I was the resident skeptic to find out if this actually was telling us what we thought it was. So this is sort of an outline of my talk. I'm going to give you a historical perspective on CEST, and then talk a little bit about the two-site exchange model very briefly, talk about quantitation, which is critical, and then talk about GAG-CEST, and I'll talk about two different techniques of doing it. One technique that we used actually to accelerate this acquisition called keyhole. I'll try and explain it to you. It's an old technique. And we applied it both to cartilage and intervertebral discs. It's hard to say that at 9 o'clock in the morning when you're jet lagged. Sodium imaging as a way to validate these measurements. And then I'll talk about positive contrast if I have time. So we know that there are two kinds of these exchange agents. Bob Balaban, you'll see in a second, published a paper, a very famous paper, although this has been around since Forcine and Hoffman in the 60s, where they turned this exchange phenomena into an imaging experiment, and you could actually modulate the contrast to reflect the exchange processes. And these really are looking at NH exchangeable protons, or OH or SH, and all of them have been reported. These are kind of difficult to do because they're exchanging with water, and everything I'm going to talk about was done on clinical scanners. And there's a big challenge, as you'll see, in translating this into the clinical arena, overcoming some of the B0, B1, and other problems. And then there are the Paracest agents with Silvio Amy, who was a pioneer, and Dean Sherry. And these are lanthanide complexes with very slow water exchange, which we thought historically for years were useless and good for nothing, but in fact turned out to be very powerful, and Silvio will show examples of how to actually, I hope you'll show examples. No, you won't? Okay, well, I'll show an example. So this is the paper that I talked about. This is the very famous Ward and Balaban paper, and what he looked at is these molecules here that have NH exchangeable protons, and they're pH dependent, which isn't shown here. And on the top, you have what was called a Z spectrum, where what you do is you take you make a plot of the signal intensity change as you sweep the frequency through different frequencies, going from positive to negative. And you can see there's a resonance for the NH, which you can see there. So when you irradiate the NH proton, because of exchange, you see a decrease in the water intensity, and you see it very specifically at that frequency only. And he went on and showed images of this that were pH sensitive and barbituric acid, and you're welcome to look at this paper. It was published in 2000, 11 years ago. And this stimulated a lot of interest in this particular area, which we'll go and talk a little bit more about. So how does this work? Well, there's a two-site exchange. It's well known that MR is very sensitive to exchange phenomena. So if you saturate this NH proton, and its exchange rate is in the right regime, and the T1s are favorable, then you'll see an amplification effect and a diminution in signal intensity of the water resonance. And so your image contrast, if you make an image, will reflect this exchange process. And so this you can, if you do this correctly, there are equations that are simplified. They're the modified block equations. It depends how many pools of these you have. There are 2-site models, 3-site models, and 4-site models. But these can be modeled, and you can predict the change in signal intensity over many, many ranges of parameters that are experimentally accessible. If you can't solve them analytically, you can solve them numerically and actually get the right answer completely. So I like to show this slide because this is Dean Sherry's slide, my now colleague and old friend, where he found this europium complex. I think this is the tetraglycinate that he published, and this is what happens in an annular phantom. The outside has water, the inside has a 60 millimolar concentration of this agent, and when you saturate the water, you see a decrease in intensity. And what's nice about this illustrates a very important aspect of these contrast agents, is you can turn them off and on externally with an RF pulse. So if you don't saturate them, the contrast is relatively normal, unperturbed by the contrast agent. When you actually activate them, you can selectively activate them. And if you put 2 or 3 of these in that resonate at slightly different frequencies, you can measure multiple different processes at the same time. So one of the things that we were interested in as we applied this in vivo is one of the sort of challenges is determining if you use one of these agents, particularly an exogenous agent or even an endogenous one, you'd like to determine the concentration somehow. That's really the holy grail. You're actually trying to find the concentration of this agent in vivo, and it's not so simple. And so we actually developed a method which we think will work in vivo, and we published this in MRM a couple of years ago. And this is an approach that Tom Dixon developed, one of our collaborators. And in order to do this, you have to know that if you want to measure the concentration, you have to measure the exchange rate, and you have to measure it in vivo. Now, we know that there are many ways of measuring exchange rates using NMR techniques. And here's an example where you can measure the exchange rate from the line broadening of the water residue. This is a paramagnetic tetraglycinate compound. And you see the temperature, the experimental spectra are on your right and the fitted spectra on your left. And you see the temperatures on the side and the exchange rates beside the fitted spectra. And what we discovered when we did this is that the temperature dependence is very high. Now, what's interesting is we used to measure the exchange rate at 21 degrees and assume it didn't change when we went to 37 degrees. But you can see there's a huge change in exchange rate with temperature. It almost changes by more than a factor of 2. So in vivo, we developed this method. It's again an MRM. You're welcome to look it up. And what this allows you to do is actually plot 1 over the B1 of the irradiating frequency squared, and the x-intercept gives you the exchange rate. And if you compare back to what we saw from all the classical ways of doing this, there's another way to measure the exchange rate, and that's by fitting the Z spectra. You actually get agreement. So you can apply this method in vivo. You have to take several images at different B1 irradiations, measure the signal intensities, and looking at the x-intercept, you can determine the exchange rate, and from that you can measure the concentration. So this is a method that we think will work in vivo. We called it, I was going to call it a Dixon plot because Tom Dixon developed it, but he's a very shy guy, so he insisted we call it an omega plot. So that's what it's called. So I'd like to move on and talk about Paracest, and I use this as an example, number 1, because it's important, and number 2, because it allowed us to do some methods to accelerate the acquisition, which I'll talk about. Now, why look at GAG? Because collagen in this case, and I was kidding with Gary Gold, this is his favorite organ. Collagen is a very highly structured tissue, and it has these proteoglycans in them, which if you zero in are very negatively charged. And what happens when the cartilage gets degraded is you degrade the proteoglycans. And so you can actually, if you could measure GAG by looking at this exchange, and GAG has exchangeable protons that you can identify, and people in the audience did this long before I did, you can actually try to quantitate GAG in vivo non-invasively. And so here's the chondroitin 6 sulfate. There are the exchangeable protons that you can see. And if you try to measure these, there's both clinical and physiological relevance, both in osteoarthritis and in disc degenerative processes, and they become progressively harder to do. Osteoarthritis is the easy one, discs are hard to do, and I'll show you some data from in vivo discs. So Paracest, if we could make it work in vivo, would provide a direct and selective measure of this concentration. And so there are many ways of doing it. Again, other people in the audience, Ravinder Reddy and others have looked at T1 row measurements. There's Degemerich, which makes use of the fact that when the gag is intact, it's negatively charged. So negatively charged contrast agents don't enter into the cartilage. When the negative charge goes away as the gag is degraded, and by the way, what balances a negative charge is sodium. And so one could make the argument, a very good one, that as gag gets depleted, the sodium signal should go down because it becomes less negatively charged and requires less sodium to balance the charge. Sodium imaging is a way that people have looked at it. We use it for validation purposes, and chemical exchange measuring gag tests is what I'm going to focus the next few minutes on. So what are the practical challenges of doing this? SAR and software limitations and hardware limitations. So SAR is the amount of power you need actually to make this work, and there are FDA guidelines about what the maximum allowable power is, and you can't exceed that power. There's small chemical shift differences between these exchangeable protons in water, and so all of a sudden the homogeneity becomes very important. And if you're doing this in an image, not just one small region, it's really... then you have to fix the homogeneity over the whole volume, and there are techniques of doing this. There's B1 inhomogeneity issues, which you have to overcome, and then motion is always a problem in vivo. So this is sort of the technique that we used. We wound up using a method that Peter Van Zyl published on called Wasser to do the B0 correction. What you do is actually you do sort of a Z spectrum, pixel by pixel, at very not high frequency resolution. You measure the center peak of water, you align everything up and do it. Again, it's a technique that's been published and just well described. And we use, in this case, a gradient echo acquisition. Later you'll see some fast spin echo acquisitions to start off with. And the reason we do this is that you can think of this as when you do the saturation, it's a preparation, a magnetization preparation step, and the image sequence is a readout, and you can use any of the faster imaging sequences as readouts to actually make an image of whatever signal intensity you've created. So this is a rough outline of the parameters we used. Here again, to remind you what this looks like, this is the Z spectrum or CES spectrum. So if you saturate here, you should see this is the so-called the on resonance. There's an off resonance control when you take the difference of these two and correct it for some asymmetry parameters to take care of the MT effect, which I'm not going to talk about too much. Then it shows you how much exchange you have. So that's the off resonance. So here's an example of gag cest. I can't see it very well in articular cartilage. You take an anatomical image and overlay the gag cest. It should show up, and you can see it here. It's not a very large effect, but it's measurable, it's repeatable, it's a few percent. And this was done at 3T in a normal volunteer. And so here's an example of how you do this. You do an off resonance, on resonance, and this is the so-called MTR asymmetry plot. You see the little green bump. That's the resonance frequency at which the exchangeable protons resonate. When you irradiate them, you see a diminution in intensity of the peak. Now, unfortunately, this is Elena Vinogradoff's cartoon about how slow this process is. It requires two separate acquisitions, actually three. It requires an acquisition for the B0 correction and two acquisitions, one where you radiate on resonance and one where you radiate off resonance. And so it takes a lot of time to make this image. And she knows I'm very impatient, so I always ask her, how can we make this faster? That's my role in this whole process. So the first thing she did is she put some wheels under the turtle. And then she put a rocket to the back and made it go faster. So how do we do this? We used an old technique that's been around for a long time called keyhole. Now, for those of you who don't remember keyhole, it was one of the first techniques that was reported on for dynamic contrast enhanced MRI and even magnetic resonance arteriograms. And so the idea is if the only thing that's changing is the signal intensity, then that's reflected in the center of K-space. And the spatial frequencies are out at the edges of K-space. And so if you take a high-resolution, non-contrast image, and you cut out the middle, that's the keyhole. And now what you do is you just sample your whatever contrast you want only at the center of K-space, and somehow you fit these two together in some way so it doesn't cause you artifacts, and that's the so-called keyhole. I'm simplifying because it's a little more complicated than that, but that's actually what you do. So you wind up taking these images, and you can do them both for the acquisition and for the Wasser correction. And if it works, and you can speed this up by a factor of 2, all of a sudden you've decreased the scan time by a significant amount of time. Now, one of the things I don't have time to talk about is you can combine all these techniques with parallel imaging if you have enough signal to noise and sparsely sampled compressed sensing, if you have even more signal to noise to burn and have a person who understands how to do this. So in principle, you can really speed this up, but I'm only going to talk about keyhole today. So here's an example of a standard CEST image. You can see the green a little better here, and the cartilage sort of overlaid onto this knee image. And here's this is a 13-minute scan time. You can reduce the scan time by a factor of 2. What you lose here is the high-resolution areas, but the center areas are actually pretty good, pretty well preserved if you use the keyhole technique. Now, the trick here is how to combine these two. If you combine them in a way for those imaging people who understand this so that there's a big discontinuity in signal intensity, you get artifacts in your image. But if you scale them properly, and that's where the whole secret here is, you can do this and you can actually speed up the image acquisition quite a lot. And so these are some of our processing protocols to go faster. We went to a fast spin echo technique, so we sped up the acquisition over a gradient echo. We do echo train lengths, and we can fool around with how well this works. And this actually gets us to the keyhole are the wheels, the fast spin echo is the rocket. And so here you can see something sped up 6.4 minutes, and you can go faster. And you can actually see that the Paracest values, which are not large, are preserved. When we compare them, going through all the steps to accelerate them, they don't change very much. It's still in the 1% region here. If you go too fast, in other words, if you go 4 times faster, you wind up actually losing. So there's a limit to how well this works, and it's probably a factor of 2 in keyhole, which is significant here, because you're going from something like 13 minutes to 6 minutes. So the keyhole CEST, we think it has some advantages. In particular, you can still apply it to the other techniques that speed up acquisition, like parallel imaging and sparsely sampled compressed sensing. So I'd like to move on and talk a little bit about the disc. Now, in humans, the disc is made up of 2 regions, the nucleus pulposa, which is in the middle, and the annulus, and I can never pronounce the F word there, so I'll just call it the annulus, the outside part. And they have different organization levels, and they have different amounts of GAG in them. And as the disc degenerates, the GAG concentration goes down, and it should happen as a function of age. So you see it here again. You have these lamellar structure in the annulus, and in the nucleus, it's far less well organized. And so here are some first examples. This is an intact bovine disc taken out of a cow. That's what bovine means, I think. And you can see that there's a difference in the Paracest concentrations of the annulus and the nucleus. And so here's our first normal volunteer. Actually, we did 2 of them. And you can see that if you look at the nucleus pulposa, the GAG concentration of the Paracest values are about 5%, 5 to 6% in the middle. And on the outside, they're almost 0. And so you have a way of actually measuring. And these are the images overlaid here on top of the anatomical image. And so you can convince yourself, even a skeptic like me, that this is real. And if you repeat it in a bunch of normal volunteers who are young, you get numbers like this pretty reproducibly. So we went ahead and did a bunch of different volunteers. This is our very early results, done on different ages. I'm not Gil, we need you here because I think you're at the other end of the age scale here. We only found a 70-year-old, so we need to put you down in the 75-year-old to study you. But you can see that the GAG concentration does change with age. Now, again, it's very important to to validate your measurements. So how do we validate this? We do it against sodium signal. Now, measuring the sodium signal in a disk is not easy. It took us a long time to get to the point where we could do it. And here's a sodium signal interpolated and filtered of the disk, overlaid on the same thing. We graphically prescribe it off a proton image, we do the GAG test, and then we switch over and do sodium. It takes about 12 minutes of acquisition, and you get an image like this. Here's some other examples. This is age 25, age 70. What you don't see here, because we've blown it up, is we can put a vial with a known sodium concentration in the field of view, and we can reference the sodium concentration to it. And these are scaled to that vial, and so you can see that the sodium signal does go down in the older person, just like the GAG does. So that makes you start believing that this is a real effect. And so again, it'd be nice to be able to measure all the disks. Right now we can do them 1 or 2 disks at a time because they're obliquely angled. That's really a problem for us. And so here are the ratios of the sodium signal. We put them side by side. You can see age 21, age 25, age 70. Again, reference to the external vial. And so you do see a decrease in sodium signal as a function of age. So the last thing I'd like to finish with in the last few minutes is all of the CEST experiments that we did were negative contrast. In other words, you see a drop in signal. Now, there's some reasons to get positive contrast. There are probably a variety of reasons to do positive contrast. So Elena and I talked about how to do this, and actually it's easy to do this in an imaging experiment because the T1s are dependent on the exchange, and if you saturate them, this again goes back to Forcine and Hoffman and people who do exchange, you can actually generate positive contrast if you do sort of a very fancy inversion recovery sequence in the presence of irradiation. So this is the pulse sequence. You give an inversion pulse, and you set it so that it nulls out the background signal, which is known. And you can do multiple of these, so you get very nice background suppression. That's important for 2 reasons. 1, it decreases the sensitivity to motion artifacts, and 2, it gets rid of the background MTR signal. It really suppresses it. So then you use an imaging sequence, a fast imaging sequence, and in the gray part, you either irradiate on frequency or off frequency, and you take an image, and you can actually get quite a nice signal intensity difference if you do this right here at the optimal B1 field. And that depends on the exchange rate of the protons. So if you do this, you can actually make very nice images of, now this we've only done in ex vivo cartilage, and here's the positive CEST, and here's the negative CEST, and you can actually see you get slightly lower CEST values, but the background's completely suppressed, and that has a big advantage in vivo. So my summary is, in spite of all the challenges, CEST is possible in humans. You can accelerate the acquisition using a variety of different techniques. You have to be careful because if you go too fast, you begin to lose this small signal. Positive contrast has some advantages, which I think are yet to be completely exploited. Now, again, I wanted to figure out, it's your birthday. What do you tell someone on their 75th birthday? So I just moved to Dallas, so I didn't know the rabbis very well. So I found this Dallas rabbi, and I asked him, what do you tell someone when they turn 75? Anybody here speak Yiddish? Bis 120. Right? So for those of you who don't know what that means, till 120. Happy birthday, Gil, and thank you all for your attention.